Hey guys, I'm back. So there has been a bit of an issue with YouTube and the previous link that we shared. So I created a new live stream where this whole conversation will get streamed to. This is a very deep issue from our part, and I'm trying my best to spread the news as fast as possible. So let's just get started with the event, and I'll be spreading the information all around the internet, if that's okay with you.
Okay, Adrish, can I start?
Yep, you can start.
Okay. Okay.
So I have a
Good evening,
question. I'm so
everyone.
sorry.
This whole
Yeah,
server.
you're right. Yeah.
So because I prefer this like presentation to be shared with the other people too. So are you gonna so what is it? Like are you
Yeah,
gonna record it and then
Adrish,
put it? Okay.
yeah, Adrish is just preparing another link because this link is creating some issues. So we're just
Okay.
preparing another link and getting it shared everywhere as soon as possible.
Thank you
It's
so
just
much.
okay.
Sure.
Okay.
Okay. So Adrish, I'm starting, right?
Yep, you can start.
Okay. Uh,
Because I prefer this.
I would like everyone to please put your microphone on mute. Thank you. Okay. Good evening, everyone. I welcome you all to today's webinar session. GNX presents Deep Learning in Space. Today's session is going to be pretty interesting because we have someone with us who is going to give us a drive into the space. Amazing, isn't it? Okay, so let me give you all a brief. NASA is planning to return astronauts to the moon, sending them to Mars, and exploring moons of Jupiter and Saturn soon with self-navigating spacecraft. In this mission, spacecraft should be as autonomous as possible with low cost, size, weight, and power consumption. Hardware that must have real-time decision-making capabilities. Although existing autonomy platforms on Earth can master a complex skill from scratch, provided sufficient computation and data, this is not feasible when a spacecraft has limited resources and needs to deal with a wide range of environments. Achieving self-navigating spacecraft requires both autonomy within the onboard system. Okay. So I think I'm giving a lot of explanation, but I think that it would be better if the person who is with us today explain the rest of the part to you. So who we have with us today is Dr. Shahruz Ran Alimo. He is a lead scientist at Jet Propulsion Laboratory, California Institute of Technology's Deep Learning Group. Prior, Ran was a postdoctoral fellow at the Caltech Center for Autonomous Systems and Technology, working on spacecraft formation flying. His primary research interests span theory and practice of non-convex optimization for machine learning for autonomous systems. In particular, he has been working on the development and analysis of deep learning algorithms for teams of spacecraft and ground data systems, which can cooperate to form virtual structures and networks and can perform distributed measurements and computation that is usually not possible with a single agent. Dr. Alimo received his BSc degree in computational mechanics from Sharif University of Technology in Iran and the PhD degree in computational science from University of California, San Diego. He was awarded the gold medal for Iranian Astronomy Olympiad and UCSD's Outstanding Graduate Students Award in recognition for strong research initiative and leadership skills, and the JPL's Voyager Award in recognition for the development of innovative optimization algorithms for deep learning technique to accelerate automation in mission operation systems. So before we have Dr. Alimo with us, I would request our principal sir of Netaji Subhash Engineering College to give us an welcome note and welcome Dr. Alimo. So I would request principal sir to please give us an welcome note.
Thank you. Thank you
Yes,
very much.
yes, sir.
Yes, Dr. Shahroz Ran Alimo, lead scientist at NASA Jet Propulsion Laboratory, and our keynote speaker of today's webinar, Deep Learning in Space, Dr. Piyali Chatterjee, HOD, Department of Computer Science and Engineering, other distinguished professors, faculty mentors, and student coordinators of GNX. the official Linux group of CSE department, and my dear audience, ladies and gentlemen who are watching this live show around the world, a very good evening to all of you. We have gathered here in this August gathering to welcome Dr. Ryan Alimo and awaiting eagerly for the forthcoming wonderful webinar session on deep learning in space, smart mission operations, and optimization multi-agent systems by him. On the behalf of Netaji Subhash Engineering College, I, Professor Dr. Tirthankar Dutta, Principal of this institute, would like to express my warm welcome to Dr. Alimo and extend our sincere thanks for his sparing valuable time from his busy schedule. A brief introduction about our college. NACC is AICTE approved Makaut, the state university affiliated, one of the pioneering degree engineering colleges of Eastern India. The institute is accredited by NAC, and our engineering programs started receiving accreditation from NBA, National Board of Accreditation, that is the Indian version of ABET, since 2005. The institute is beneficiary of prestigious World Bank Fund TechUp 1 worth rupees 7.5 crore and was ranked second best among all the colleges of Eastern India in terms of performance. The institute caters more than 3,500 students in different disciplines of engineering, technology, and management. Now, I would like to take the privilege to introduce our keynote speaker, Dr. Shahraz Ryan Alimo. He is a lead scientist, as already mentioned by our anchor, in machine learning at the Jet Propulsion Laboratory of the California Institute of Technology's Deep Learning Group. His research interests include span theory and practice of black box optimization for machine learning. He is a postdoctoral fellow at Caltech Center for Autonomous Systems, and he received his BSc degree in computational mechanics from SUT in Iran and PhD degree from computation in computational science from the University of California, San Diego. Presently, Dr. Ryan Alima is the lead research scientist at the Mission Control Systems Deep Learning Technology Group, NASA's Jet Propulsion Laboratory. At the end, I welcome once again all the participants and expect that at the end of the program, all the participants and audiences will be immensely benefited from the inputs received from our eminent rocket scientist. Now, sir, the stage is yours. Thank you. Thank you very much.
Thank you so much, sir. Thank you for your valuable addressing. And now we will start with Dr. Alimo with us. Before, I would just like to give a brief introduction about what GNX is. GNX is the official Linux group of Netaji Subhash Engineering College, which is an open source community of Linux loving enthusiastic people. It was Sir Richard Stallman who has inaugurated the Nixel group of NSCC, and today we have developed Nixel into GNX. The various wings of GNX include, as you can see, competitive coding, hardware technology, data science and AI, web and app development. And GNX welcomes Dr. Saharus Ryan Alimo once again. And Dr. Alimo, the stage is all yours. Thank you. You can share your screen, sir.
Okay, yeah, thank you so much for all the kind words that you mentioned, and I would like to thank each and all of you, especially Audrey for the invitation, some Dutta for the introduction, Professor Dutta for also the kind words, and all of you in GNX and NSEC. So it's a great pleasure to be here. My name is Sharud Ryan Alimo, and I guess you covered a very good introduction, so I'm not going to go over it. But here is the photo of JPL. So that's the historical place that the first American, satellite was designed and launched from this area, and this is my workplace. We are remote, so I cannot go there this time. I'm working from home, but I used to be there. I'm gonna go back there after this pandemic is over. So today's mm, presentation is titled "Deep Learning for Space, Multi-Agent Systems, and Smart uh, Mission Operations." Uh, as you know, we had the I'm sorry. I guess let me. Is my voice okay? Can you hear me well?
Yes, absolutely, absolutely. We can hear you
Okay, okay,
properly.
okay, cool. I was just worried that, yeah, my voice is not reflecting. So, as you know, we landed on the moon in 1969. That was one of the high points of NASA and even humanity to go and become like not multi-planetary species, but putting, going to another planet or another moon outside our the Earth. But we did it using computers that are so primitive that we would not even notice them today. Apollo 11 was landed on the moon when the most powerful computer on Earth was more than 1,000 times less powerful than cell phones that you have on your pocket. And when we go and see the space, even right now, this is not like the Moore's law is not valid for the space missions. The RAT 750 is one of the state of the art, like, one of the things that is being used, like rat hard, it's called, like, they're very uh, strong when you have radiation, and they can do the computation, and you have like strong radiation in deep space. So this is being used in spacecraft and Mars rovers. However, as we see with the private industry and some of the work that we're having in the coming years, this is being shifted. So we're going to have a new rover, like a new helicopter on Mars, that is much more powerful than the rover itself, and it's using off-the-shelf, computer computational power, and the processors that that we're going to see that whether it's going to work or not. Many companies are working on that. This is going to be a test, and if it is successful, then there is a new avenue for exploring the deep space, right? So when we talk about the limitations for the deep learning, one of them is the computation limits that you have. You cannot do a lot of computation on board. The other one is validation and verification. Also, it's called explainability. So you want to be, when something goes wrong, you should be able to verify it and validate what happened. There is also the problem of battery budget and battery consumption, because these algorithms usually need a lot of power consumption, and you don't have that capability when you are in deep space. Uh, Another problem is lack of training data, because those areas like Mars or other places, they're very different from what we have on Earth. And the other one, the cost, the weight, and the size of these processors, that if you want to do online training and deep learning in space, that's going to be an issue for you. Just for your information, this is called Ingenuity. The Perseverance is the rover that both of them are going to be, on Mars next year, February 2021, less than a year. So the outline of the talk today is going to be three parts. The first part, I'm going to go and talk about, multi-agent systems and formation flying. And the second part is going to be the communication, how we do the communication with the spacecraft outside in deep space. And the third one is how we can monitor them. And in all of these, we're going to see um, how deep learning can help us. The swarm systems enable us many new capabilities that can result in breakthrough in sciences. One of these multi-agent systems that we know and we are working on is called Starshape. So this is a future Starshape mission that involves in like two spacecraft. One would be a telescope, and the other one is gonna go and cover, a very far distant star, and these two are about, like, let's say, very very far from each other, like thousands of like kilometers from each other, and you need to have very accurate relative pose to be able to identify exoplanets, the planets that are outside our solar system. And in order to achieve that, and these are the swarm of the spacecraft that they can create a virtual, objects and do more science work. And this is called Sunrise, another JPL futuristic project. So when we talk about relative navigation, there are two factors that are important for us. The first one is the accuracy that we need in order to perform our mission. The other one is relative distance. So there is a trade-off between the accuracy and relative distance. If you want to do docking and rendezvous, you need a very high precision, and the distances are low. And as you go to the formation flying, that is, I'm sorry, I don't know what happened. The formation flying, you're going to see that the distance between two objects and the agents are going to be about a kilometer or like hundreds of meters, and we need less. The accuracy is going to be like constellation is like a GPS, and swarm and fractionated spacecraft are like tiny spacecraft that are going to create a virtual structure. So my research area is more focused on the formation flying, and swarm and fractionated spacecraft. Also, it has some applications for rendezvous and docking, but mainly it's formation flying and swarm of spacecraft. When we see this, when we talk about swarm and hundreds of or thousands of spacecraft, we each of them needs to be cost efficient. So in 2008, we launched a RainCube, which was a low Earth orbit CubeSat that was able to provide like it's a 6U, we can call it. A lot of like complex scientific research using the radar, and we also have the Marco, which was again a technology demonstration that went to Mars on 2018 with the InSight spacecraft. So these missions showed us that off the shelf, let's say, units or the hardware can be used to do even complex scientific work, and we possibly can extend them to hundreds or 10 or a multi-agent system that can work one with each other and perform a complex task that used to require a huge spacecraft to do the same work. However, autonomy and artificial intelligence and the control of these like how they need to work with each other is really important. So one of the elements that are important is relative navigation. It means that what is the distance and rotation of one object respect to the other one is. This has different applications, right? If you want to in-orbit assembly and you have different objects, you may have unknown objects, also like here, and you can estimate their shape. So you need to be able to accurately find their relative distance, relative velocity, rotation, and other things to be able to perform your task. However, all of these needs to be autonomous and on board. Sometimes you don't have time to do the calculation on Earth, and it's not going to be feasible for you to do some of the things remotely and then send them back to the spacecraft. When we see the relative navigation approaches and scenarios, we're going to have different types of sensors, right? We can have a stereo camera, we can have molecular camera, we can have LiDAR, time of flight sensor, GNSS, radio frequency, star tracker, based on whether the object is known or unknown, uncooperative or cooperative. You can have passive or active, you can have different approaches. However, what we consider is, in fact, using the monocular camera, because they're low in power, they're cheap, and they can be used for different applications rather than just like other than relative pose. This is one of the experiments that was done in NASA Goddard, and here you see that how the data set is being created. So this is a complex and expensive, hardware that is having an object like a spacecraft model inside this object, and they're putting different illumination conditions, different backgrounds to make the computer vision algorithm robust, different illumination conditions. However, this approach might not be generalizable, but the main challenges that we see in computer vision space is unfavorable illumination condition, low signal to noise ratio. So this is the Prisma mission. You see that suddenly after some frames, your the whole situation is going to be different. The other one, the other challenge that we have that is different from the problems that we have on Earth is the background and foreground segmentation, as well as we have some noises in the images, even in the cameras. So that's gonna make the problem of detection harder, because in each image you have different sort of noises. And the first work that we have done in 2019 was developing robust feature extraction algorithm, methodology to known but uncooperative objects, such as these two spacecraft. One of them is called Mango, the other one is Tango. So Mango is taking a picture of the Tango spacecraft. So in this in here we see that the objects are around 50 to 5 to 50 meters apart from each other. So in here about 20 meters, and you see that our new algorithm that we describe in this paper, we can detect the polylines or the lines in the spacecraft, right? This is not based on deep learning, and these are like regular computer vision techniques that we use. And again, in different conditions, if you have even the object is very far from you, you are able to get some sort of matching the features that you have with respect to the real model of the spacecraft. However, as you may notice, this has a lot of limitations. So it is really hard to generalize different projects and also spacecraft. So you need to do a lot of hand engineering or to make an algorithm robust to a specific mission. Therefore, our new the other approach that we had was based on convolutional neural networks. So when we talk about the computer vision, the first thing that comes these days is CNN and convolutional neural networks, right? And they are really good in order to do the classifications, like most of the available CNN. But one of the things that they are not good at it is in translation and rotations. But during the past few years, we see that there are a lot of good architecture, PoseNet for robotics. They have been developed, and even there are a lot of progress during the past 2 years in using convolution neural network for pose estimation of spacecraft. So one spacecraft is taking picture of the other spacecraft, and we want to understand that what is the translation and rotation look like. So here, this is one example. We had a number of thousands of images in different scenarios. We had asymmetry satellite, and we wanted to see what's going to be the relative pose, which means that translation and rotation of the spacecraft look like. And here is our result that if you use like branch VGG19, like this was like an old result. We also have parallel VGG19 that we describe in the following papers. It's going to improve the performance of relative pose estimation for known but uncooperative objects, like in-orbit assembly or formation flying of like spacecraft that you can only take a picture of them. And one of the techniques that is commonly used in computer vision is transfer learning in order to reduce the number of training variables that we have. And we were able to successfully show that transfer learning is going to be helpful to do this computation. However, we talk about all of these, right? The other question that comes to your mind for now is, okay, we have done these extensive, calculation and pre-trained model. We have very good model in the simulation environment, because simulation are cheap, right? You can have 12, when you have the simulator, you can generate as much as you want, like the data sets, right? However, you need to be careful about overfitting, because if you overfit to your training data set, then generalization is going to be hard. So in this ESA, European Space Agency Pose Estimation Challenge, they had 12,000 simulated images. Then they had 5 real images and wanted to generalize to 300 real images from the Tango, like a Prisma mission. That these are the real images. These are the again, the camera images, and these are the images that were created inside the gaming engine. And this is the challenge. Many people try to use different CNN architecture. They were really, strong and impressive in order how they can predict the pose of spacecraft, right? Even in the sub-degree accuracy. However, in some situations, we see that the solutions are high confidence and low confidence. And in some scenarios that you expect to have high confidence and you expect to do good, you observe that they might not perform well. And one thing that is really important in space is validation and verification challenge, especially for deep learning algorithms. In other literatures, like deep learning literature, we also call it explainable AI or XAI. And that's about how we can diagnose this deep neural network. So this is the paper that we had, and we briefly talk about one approach that we can diagnose the CNN for the pose estimation of the spacecraft. But why we want to do the pose estimation? What are the other applications of that, right? So if you have the swarm of spacecraft and you have unknown, objects like a cloud, then the problem also becomes challenging, right? And deep learning is going to be very useful. Or if you have a swarm of, multiple agents around an asteroid that is unknown object, and it can have a random shape that, again, using multiple view for this and seeing one object is going to be helpful, and also reconstructing that is another area that is really important, and we need to investigate more, and we are working on that. And so as a summary of part 1, we see that multi-agent systems and distributed systems and formation flying enable us new kind of science missions. The preliminary results were presented, as you saw, on different applications, Tango spacecraft and Prisma mission, and also in orbit assembly. And the challenges that remain in order to use deep learning for real missions is the SWaP, also like cost, size, weight, power constraint, or SWaP constraints, lack of training data in space. So that's also an open area in AI and machine learning, how we can learn with few data, few shot learning. Like also it can be considered, right? But even the few shot learning needs more data than regular supervised learning approaches. Like semi-supervised we can consider, but this is still open area, and it needs more research to be done in this case. Also simulation to real, that's another area that we need to investigate and see how we can generalize from the simulation to the real world scenario, and use the high fidelity model for in operation rather than low fidelity. So create a trade-off between low fidelity and high fidelity models. So to sum up, this is one of the work that I did during my postdoc. We had a swarm of drones on the top, so it was following one of the robots. It's called Cassie, and that was one of the beginning, the beginning of my work. And these days we're working on the spacecraft, like hundreds of agents, rather than just having like 4 or 5 or 4. But these are all active area in order to do more research, right? So the other area that I want to cover quickly is the communication. How we communicate with the spacecraft, outside our solar system. So there is something that you may heard about it or not. It's called Deep Space Network, or DSN. DSN are a set of arrays of antennas all around the world. In fact, there are three places. One in California, one in Madrid, and one in Australia. And these spacecraft are communicating with all the missions that we have outside our like the orbit of the Earth. And here are the locations of them that you see: one California, Madrid, and Australia. And these are 120 degrees apart from each other in order to see everywhere in the universe, right? In order to cover all the parts. And if you wanted to see what data we are getting right now, you can check out this link over here, and you see what sort of data we are getting from space. However, this problem, the DSN has a challenge of oversubscribing. As we have more spacecraft and launching more to the deep space, we see that these antennas that are all around the world, these are 3 complexes, and each complex have 34 and 70 meters antennas. They seem to have, like, in some scenario, even 60% oversubscription, which means that you cannot cover all the requests that you have from the missions that you get. And as a result, what we want to do, we want to use AI and optimization and deep learning to make this large scheduling problem automated. Currently, there are a lot of human, in the loop, and they're like negotiating between which mission needs to be scheduled and which missions needs to be, needs to be prioritized. However, as we have hundreds or thousands of spacecraft, right, in all around the universe, then that problem is going to be outside of human capability, and we need to do some sort of automations that are reliable, explainable, and accurate. So when we see the data, for example, this Mars Express orbiter, which is around Mars, so it's going to look like this. And then when we have the structure data, this is like in 2018, we see this is only for one mission. It's going to be that crowded. Imagine that if you put multiple missions, you're going to see that how crowded is going to be this schedule, and each of them are one of the antennas that we have. And NASA owns all of these like sequence of the antennas, like deep space networks. The area that I'm working with a colleague of mine at University of Texas Arlington is how we can use parallel optimization platforms that are capable with GPUs and TPUs, and we can solve this large optimization problem more efficient. So here we show some preliminary results on how our performance looks like to the state of the art on linear programming and quadratic programming. So exponentially, we are like at least like order of like 10 to the 100 times faster than the existing algorithms, and one of them is because of the way that we can parallelize with the GPUs, also different relaxation problems that techniques that we are using to solve this large scale, non-convex, non-linear optimization problem. The other approach that is being used is how we can use deep reinforcement learning, right? Deep learning are good for the situation that you have high uncertainty and large, scale problem. And you can have the agent that is trying to find what would be the optimal set of schedule given the constraints and the request and the environments that you have. And here is like a demo of how this scheduler can look like. So as a summary of part 2, we understood that parallel computation and smart sampling is really important, and it can solve some problems that possibly require a lot of human in the loop and are somehow very hard to solve with the existing off-the-shelf tools. So we need to create customized, solvers for the problem in hand, and in order to use deep learning, we need to have simulator engines like environment, and in order to solve like the problems efficiently and generate the training set, like as we know, so we can use the advanced optimization algorithms and non-convex optimization algorithms, such as semi-definite programming and convex relaxation, conic relaxation, parabolic relaxation, to tackle these large optimization problems. However, the problem that again remains, and the challenges that we have, is how to generalize the actual mission, right? And if you use deep learning that uses the training data from the simulation and maybe many like the data set that was for 2 or 3 years or 5 years ago, there are some differences, right, in the training set, and how we can generalize with few samples. Another approach is going to be hybrid approach we are considering, and other than that, we're going to see that at some time, maybe in 50 years or so, all these problems needs to be done in another processors, right? Then we need to again develop new set of algorithms, such as like quantum computing. But we are very far from, like quantum computers are not efficient at this point in terms of how large you can solve the problems, right? But in 100 years, we may see that, the standard computers are going to be like something like that, like quantum. And the other area, the third area that I'm going to go over it is mission operation, right? So please note that we had three areas of automation and deep learning for space. One was onboard autonomy, right, in space. The other one that I talked was communication, how we can communicate from the Earth, right, to the spacecraft. The third one is mission operation, which means that if you have the data, like if you have the spacecraft, some of this data needs to come back to Earth, right? You need to send the data to Earth. How you can do deep learning, right, on the mission operation and on Earth using the clouds, Google Cloud, AWS, Azure, whatever you want to think about that, right? So you have unlimited resources on Earth, and how we can use these great computation power that we have on Earth. So one of the things that exists is this is the Mars 2020 or the Perseverance rover that we have, and this Perseverance rover, you need to predict how much energy you're going to consume, right? How much energy you have each day, and this is a problem that you need to know in advance, because if you don't know, you don't know how much science you can do each day. So you have prediction models, right? You can predict how much you're going to generate, how much energy you have, but sometimes when you see there is an error between how much you can even you have energy compared to the models, and that can be because of the shadow that exists, or it can be a number of different reasons, right? That you may observe, and we want to make this problem and this energy consumption of the energy for the rovers more reliable. By the way, if you are excited about this project and we want to help, there is a new, initiative. It's called AI for Mars, that talks about this problem, and it's and you need to you can in fact help NASA and us to label the data sets. One of the issue is the sand segmentation. So the Spirit rover got stuck in sand, and the mission got over, right? Also, the Curiosity got stuck in sand, and it had a hard time coming out. So these are something that we need to, be aware and careful. And one of the areas that I'm actively working on is data accountability in mission operation. What do we mean by data accountability? Usually, there are some losses in the data that from maybe the Curiosity rover, it's called MSL, sends the data to us. Maybe the rover, like the orbiters that are here, send the data to the DSN, and DSN is going to send it to JPL. And there's some people that are looking at the data, and usually they ask, where is my data? What happened to my data? And first, the Curiosity rover sends to the orbiters send to the Deep Space Network, then the JPL data control, and in the end, it's called Ground Data System Operation for MSL. And you want to know where the data is missed, right? And again, if you are excited about this work, so we just published some paper in arXiv that talks about how we can use unsupervised learning algorithm in order to identify where the data is missing in this pipeline. And also we are working on the supervised algorithm, but again, labeling this data is time consuming, and we created some new way of labeling of the data and how it's missed, using the combination of the AI and the human operator that we have, the experts that we have. And this project was awarded 2 times, 2019 and 2020, by the NASA's Chief Innovation Fund. The other area that is important in mission operation is security. In 2011, 2 of the spacecraft for the NASA got hijacked, right? And we didn't have any information about them for about 8 or 10 minutes, and that's scary, right? You have billion-dollar spacecraft. You send it to Jupiter. You send it to outside our solar system, and suddenly you don't have access to it. And imagine if these people do some weird things, then the whole multi-billion-dollar mission is going to go over, right? So it is important to find out uh, like the intrusions in the system. And again, deep learning and machine learning can be used like unsupervised learning. This problem is mainly unsupervised, right? And semi-supervised to understand when the system is not doing normal and find suspicious activities. So when we talk about deep learning and machine learning, there is one problem. The problem is what your model looks like, right? So you know for computer vision that there's some standard techniques, or maybe for the speech recognition or the NLP, right? There are some standard, neural network architectures. However, when we come to a new domain, right, you don't have that insight about the architecture of neural network or machine learning, or in general your control algorithm. And during my PhD, I developed a new family of optimization algorithms called delta dogs, that stands for Delaunay-based derivative-free optimization via global surrogates. That these algorithms can, like this generalizable derivative-free optimization algorithm, considers that your problem is the objective function is unknown. It can be defined inside a feasible domain that can be possibly non-convex. So here is a toy problem that we see. So you have a lot of equality constraints, right? The feasible domain is in the black area and the white area. The objective function is non-convex, right? And it's non-linear. And you are looking for this global optimizer, this solution, right? That's a very challenging problem, given that you don't know what f of x looks like. You don't have what f of x look like. You don't know how the feasible domain looks like. You want to learn how these underlying functions look like. And some people, like, a standard approach is Bayesian optimization, but the problem over there is you may end up a local minimum on the solution that may not be safe, and it may danger, the whole system that you have. So our approach, delta dogs omega, in fact, in this paper I talked about, is guaranteeing the convergence to a global solution with few number of function evaluations compared to the state of the art in other methods. Also, we can use delta dogs for improving the control of like different vehicles. So this is the GPS model that a human is tuning that GPS model. However, using delta dogs and smart sampling, we are able to automate that task and reduce the error of the position and also the attitude. So we can consider delta dogs for auto ML, right? Automated machine learning. And as a summary of this part, we can see that deep learning tools can increase the performance of our missions, right? Especially in mission operation system, you can use cloud computing and data analytics model to help the scientists to learn more about what can be done and what is happening in the other planets. And also you can make the spacecraft somehow autonomous in terms of the data pipeline. So one autonomy, self-driving, is called like how you can drive, right, by your own. The other autonomy is how you can use the data that is coming, or how the automation of the pipeline that is coming to you, and your end users are always scientists. So how they can use that reliably. Delta dogs again is much more efficient than the Bayesian optimization. I would be happy to share the code. It's open source. You can use that for different applications you have. And the challenges that remain even in here is Still, for the new applications, we need a lot of labeled data. However, we don't have them, right? We may have, in these problems, you have a lot of data, but they are not labeled. So how we can use unsupervised learning or combination of human AI to solve these problems, these complex problems? Can we use generative models? We are not sure about that, right? Uh, but that might be one option, like semi-supervised learning. But yeah, it needs some research to in this area again, how we can use semi-supervised learning for space applications and when you have less data. And the other thing that I'm working on, and it's challenging, is how we can deal with the case of dimensionality for black box optimization problems. Because when you have like 100 or 200 variables and you want to structure your neural network and find how many layers you have, how many nodes you have, again, usually the black box optimization algorithms are limited in terms of how many variables they can handle. So as a final, you know, board and what we have is we see breakthroughs in industry, right? We saw iPhone, that was one breakthrough. We saw like SpaceX, reusable rockets, that was another, breakthrough. Self-driving cars, another breakthrough. But what is next? I don't know. But we can talk about, okay, spacecraft, again, the same scenario. Some people say the next breakthrough is going to be AI, like the general AI, right? Flyby we had in like 60s, and orbiters, we had landers, Pathfinder. We're going to have helicopter for the first time next year. And what we can say for the future of space is going to be distributed, right? We are going to have a swarm and multi-agent systems. These systems are smart, they are automated, they can work with each other, they can be, they're small, they can team up with each other and create some larger objects and overall, when you want to go to Mars or Moon or other places, you need to have like some sort of robots that team up with you and help you. So the next possibly mission that we're going to have, right, to Mars and the Moon is going to involve both robots and human. It's not only human. And we also can, and they team up with each other to maximize, the science objectives that they have and the things that they can do. Even currently, we are mostly teaming with the AI in many of the applications that we have every day. So the target environments that we're going to have, ocean worlds, right, underwaters, caves, these are the other areas that we have not explored, and we are going over them because caves are going to be one suitable place for us to have permanent, right, shelter in Mars and Moon. And here is the robonaut that was on ISS. So I'm not sure we're gonna have the robot like that going with us to Mars or some other shape of robot like Star or other things. But for sure, we're gonna see some human AI teaming. So the conclusion is the future of space is distributed. CubeSat and small satellites are getting more popular to perform the science work that we have. There are many opportunities in using high performance computing like edge TPUs, right? Snapdragon, the NVIDIA and Intel, right? All of these new embedded systems that are capable of high performance computing can help us to do more complex science work and autonomy for our spacecraft and robots. Also, we need to automate the communications such as DSN with the spacecraft and automate the pipeline that we have on Earth. And Linux is really important, by the way. in many of the projects and robotics projects, Linux is widely used and it's a standard. And I would like to thank all of my colleagues and co-workers. I would like to thank my interns that work with me, and there is a list of some of them. And yeah, so what I see is going to be, we're going to have a Mars rover that asks, okay, where it needs to drill, what it needs to do, and everything about that is going to be automated and only send a good set of like data that we have, and it's going to be working in very high uncertain environments, such as the balloons. We launched the balloons to possibly even exoplanets, and if we want to explore those, that's going to be some sort of AI that we're going to see. And I would like to thank each and all of you for your time. And if you have questions, I would be happy to answer it right now. And if you have more, you can ask me through email and Twitter. Yeah. Thank you very much.
Thank you, Ryan Alimo. Thank you so much, sir. I think the webinar was really amazing, and we really got to know a lot of things. Thank you so much. So we have a few questions for you. I would like I would like to quote them, and if you kindly acknowledge them. The first question that says is, can control of Zeno effect as a case of resolving the motion issues of the spacecraft?
Would you repeat the question again?
Yeah, I'll repeat. Yeah, sure. It says that can control of Zeno effect as a case
what is
of
Zeno
resolving
effect?
the.
I don't know the Zeno effects. I'm so sorry.
Okay. So next question that is being asked is, can you give some views on the neural tangent kernel on optimization?
Again, I'm not familiar with that terminology. So if there's more explanation, it would be great. The neural tangent, I don't know about that. Maybe it's a paper about, but if the person that asked the question can explain more, what do we mean by neural tangent, I would, yeah, possibly have some.
Okay, so everyone who are having any doubts and any questions are requested to kindly drop in fast. The next question that is being asked is, how is the total swarm of spacecraft being controlled? Does it has a static or dynamic mothercraft, or all are controlled from ground?
Wonderful question. So currently, majority of things are controlled by the ground, right? So it's heavily ground on the loop. However, what we see in the future, we're going to have dynamic environment, and in order to have deal with dynamic and active and unknown environment and with high uncertainty, we need to have onboard autonomy, and that's what an area that I'm working on, right? Onboard autonomy for swarm of spacecraft. But right now we don't have swarm in the form that we observe here. What we have is up to like 3-4 agents at the time, and usually these are being controlled from the Earth, mission operation, and give the commands from the Earth.
Thank you so much. The next question is, according to you, what level of data breach algorithm is needed to hack such a big system?
I'm so sorry. For the last question, let me make some other comments. What I meant was, especially for the rovers, for example, when you land on Mars, right? Those are all automated, and you don't have everything is onboard autonomy, right? That's a mix, but majority of that is on like being calculated and we send the information from the ground, but there's certainly a lot of autonomy for the onboard on the onboard system. Okay, go to the next question.
Okay. The next question says, how did you choose the architecture for the CNN that you mentioned in part one of the talk? Did you use an autonomous framework?
So the architecture, that's a good question. We used some of the existing architectures. We tested out different sort of architectures in order to see and study like the effect of like a pooling layers, effect of the branch layer, and other things. So we had the baseline from the existing state of the art. However, how we came up with the hyperparameters was using derivative-free optimization.
I'm sorry, Ran, I just did a mistake. The question actually asks, did you use an auto ML network, auto ML framework?
Oh, AutoML. So we can say AutoML is a generalized word. AutoML, yes, it's for the Google, right? In particular, no, I didn't use AutoML. I use Deltadogs. Like
Okay.
that's something that can be considered like an AutoML, but that's something that we used. Yeah,
Okay.
we developed.
Yeah, the last question is, what about swarm of regenerative rovers acting as a building block and forming a type of fluid rover as a whole that can take any shape and size and go anywhere, hide anywhere, and even have containing capacity to do things? Shall I
That's
repeat
an.
the question?
I didn't get the question. I understood what they said, but what is the question again?
What about swarm of regenerative rovers acting as a building block and forming a type of fluid rover as a whole that can take any shape and size and go anywhere, hide anywhere, and even have containing capacity to do things?
Yeah, that's the future robots that we have, right? So we have some sort of like we can call like a Lego shape type of robots. We can have snake type of robot. We have something called puffers, and they can create like a virtual bigger, robots. If we consider the ones that are on the ground, right? Yes, we can have them attaching to each other, but still there we don't have such a robot on Earth, right? And first we need to have something on Earth and prove it here, and then we can launch it to this space. But these are active areas that definitely we're gonna see it um, in the future, because again, these are you can replace, right? As the person that asked question, if you want to change some sort of um, sensors, or some part is defective, you can change it with the other component, right? It's like a Lego. This is highly efficient. It's really good, but we are not there yet.
Yeah, thank you, Ran. I think that's all. There are no more questions for you. So I think we're at the very end of the webinar. So now I would request our HOD.
Somdata, hello.
Yes, sir.
May I ask a question to
Yes, sir.
Ryan?
Sure. Yes, sir.
Hello, thank you, Ryan, for your very good lecture. And I have a different queries. Is there any opportunity for the institution like us for any collaborative research work to you or your organizations? Is there any opportunity? Hello?
So yeah, I just wanted to show my video. So the talk is done, so I wanted to have the video, right? And I believe so. I don't know the legal process of that, but I'm sure NASA and JPL is collaborating with international partners, right? And if there is a specific thing, yes, that's doable. And there are some programs that if someone has fellowship, for example, from a foreign country, and then there is a research, and he finds or she finds a researcher that is interested to work with them. Then they can come to JPL and do that research together. But the funding needs to be um, from the like your institute or another university that is supporting, not the government money or not JPL money. If they're
Okay,
foreign
okay,
national, if they're
okay,
US
okay.
citizen or green card holder, that's another thing.
Okay, thank you, Ryan, for your valuable information. We'll be in
Yeah,
touch through this.
yeah,
Definitely, thank you.
yeah. I would be
Okay,
happy if anyone has any questions. Just let me know. Let me tell you a story. The reason that I'm having this talk is when I was young, like when I was, in fact, 15 years old, I watched the Spirit and Opportunity landing with my dad. And at that time, I was in Iran, in Tehran, and my dad, like, we both cried, and like how exciting this work is. And my dad told me that, can I see you one day at JPL working on these Mars rovers or spacecraft? And that was far, right? I was in Tehran, right? I was in high school, but that thing came to my mind, right? And I set a goal to achieve that goal, like come to the JPL, be part of the Mars rover, be part of making this possibly big mission going to the Mars doable with these spacecraft, and I work hard at that, and then I finally end up here. However, many people helped me, right? I saw, I was reading, about the people that they gave such a talk, like what I'm giving right now. I read about their articles, and that was something that kept me motivated to have that goal. And I would be happy if someone has the goal, especially I see that they're younger generation, and you are in the stage that you are setting the big goals. I would be happy to help yeah, proper people that are working hard, and they are having mission and goal.
okay, okay.
Like
Thank
maybe
you, thank you,
help me. Some people help me. Yeah. Thank you.
thank you.
Thank you so much. Thank you so much, Ryan. I think that was amazing and that was really inspiring. Now I would request, we are at the very end of the webinar, so I'll request our HOD ma'am, Dr. Piyali Chatterjee, to kindly give the vote of thanks. Ma'am, can you please unmute your mic?
Excuse me, if you don't mind, can I is it possible that I leave, or it's like the end of it?
Yeah, that's okay. If you want to leave, that's absolutely okay. No problem. Can you just wait for just maybe 1 minute
Yes,
or two?
absolutely. Okay.
Okay, okay. Thank you so much. Yes, ma'am, please.
Thank you, Shomdatta. It goes without saying, very interesting session it was. And I deem it a great honor to propose a vote of thanks to all who have helped us in making this webinar such a resounding success. And I, Dr. Piyali Chatterjee, Head of the Department, Computer Science and Engineering, on behalf of JNX and entire fraternity of the institution, Netaji Subhash Engineering College, would like to extend a really hearty vote of thanks to our distinguished speaker, Dr. Sharauj Rian Alimo, who spared time from his busiest schedule to grace the occasion. Thank you, Dr. Alimo. And today we had an opportunity to hear your thoughts, and this will surely be going to encourage us to apply deep learning in many applications. And your ideas and elegant presentation have enlightened our minds and have shown us a new avenue of research, certainly. And we would expect your assistance in such academic endeavor always. And a special mention to our respected director, Dr. H.K. Mandal, and principal, Dr. Tirthankar Dutta, for stimulating us to do our best. I would like to thank Institution Innovation Council for being with us. I am thankful to GNX team members for their proactiveness and dedication towards organizing such events. I'm short of words for their involvement. And with a deep sense of appreciation, I thank our loving teachers in GNX team for their untiring efforts. Last but not the least, my sincere thanks and gratitude go to all participants and viewers for attending this event and making it successful. Thank you so much.
Thank you
Thank
very
you,
much.
ma'am. Thank you, Ran. Thank you, Principal Sir, Dr. Tirthankar Dutta. Thank you, all the faculties. Thank you, HOD ma'am. We will be signing off. This was Shumdatta Roy hosting the event. Thank you so much.